All right. So this is our today's topic. So for introduction, I will highlight double bonds, basically alkenes, aldehydes, and ketones, carboxylic acid and its derivatives. Triple bonds, we will look on nitrile, benzene and aromatic chemistry, as well as amides. So I know you already understand about single bond, right? Where it is two atoms that share one electron pair, right? So we call it single covalent bond, where this you can see that there is the single bond usually we denoted as single dash, right? So usually the formation of this bond we consider as single valency, right? That is required, and the atoms usually that produce single bond or single valencies, we call it halogens. So usually any atom that link with hydrogen will form single bond, right? Example like chloride, HCl, and NH3, low ammonia, right? So double bond, so two atoms that share two electron, right? So which we can see through the double dash joining, and the valency, of course, double. So the atoms that usually make up double valency is, we call it chalcogens or oxygen family, right? So like oxygen and carbon dioxide. Next is triple bond. So based on the name, so we know there are 3 electron pairs and triple covalent bond. And the atoms that form the triple valency are, we call it as nitrogen or nitrogen family. So below you can see the example like cyanogen, right, acetylene, and carbon monoxide, right? Okay, so just to recall during our secondary school, right, when we learn about this valency, how hydrogen and chloride share electron. Okay, so one pair shared with hydrogen and chlorine become HCl, right? And then if two nitrogen atoms bind to each other, so there will be 3 pairs that share electron, which will form 3 bonds, triple bonds. Okay. So just to recall, we know that carbon is containing 4 valence electrons and oxygen have 6, right? So we need to see how the atom to share the electron between, because it looks like it's not what we call this, not balanced, right? So but carbon can share one pair of its valence electron. So that's why when carbon and oxygen bind, so oxygen can share a pair of it, so it become a double bond between carbon and oxygen. Right. So just to share the history, so the double bonds were first introduced in chemical notation by Russian chemist Alexander Batalov in 1859, where he's discovered the 2 chemicals, hexamine and formaldehyde. And we will look on the double bonds, alkenes. So we know alkenes, mostly the hydrocarbon, right? That we use in industry, that they are in the form of alkenes. Which is the common one is olefins. It is an oil forming gas. So I'm sure you have heard this ethylene, right? So it is the largest volume industrial organic compound. So the bond energy, the carbon double bond is 611 kilojoule per mole. The single bond energy is less, you see. So that's why the what we call this, the bond is very strong between the double bond, right? So the C double bond is reactive, right, as compared to single bond. So the length of the double bond also shorter, right? Then ethane, for the ethylene is 133 pm, and this ethane is 154 because of the sharing electron and become double bond. So as I said earlier, double bond is stronger, right? So below is just to show you the carbon can also form triple bond in some cases. For example, in this structure, right? And we know that mostly they become double bond to form this ethylene. Right, the orbital of this double bond. Okay, I think I have shown you earlier. So basically, ethylene is a sigma and pi bonding. So on the left here, you can see the sigma bonds between ethylene, and on the right hand side, where the another bond that are formed through pi bond. Okay. So these two, the pi bond, which make the carbon-carbon bonding region to form double bond, right? And then this bonding of this ethylene. So the description about the sp2 hybrid orbitals that form this trigonal planar geometry, right? So the unhybridized of this p orbital of one carbon is perpendicular to its sp2, right, of the hybrid orbital. So it is parallel to the unhybridized of p orbital of the second carbon, right? So then it will overlap with the 2p orbital which produce the pi bond. Okay, that's why you can see a double bond that located above and below the sigma bond, right, of this ethylene. So the elements of the what we call alkene. So when we mention about double bond, so we consider it is as unsaturated. So they are capable of adding hydrogen when they are present of catalyst, right? So when the product produced, we call it alkane, so it becomes saturated. So the presence of the pi bond of the alkene or the alkyne or the ring of the cyclic compounds can decrease the number of hydrogen atoms in a molecular formula. Okay, so but each element for the formula of unsaturation, usually we write as Cn H2n, which correspond to 2 pure hydrogen atom, then saturated formula, okay, which Cn H2n plus 2. Okay, just to share with you the structure of saturated propane, C carbon 3 with H8. Right, when it converted into propane, so it lost 2 carbon, right? So C3H6 and become as unsaturated. So now we look on the commercial importance of these alkenes. So there are important intermediates, for example, that being used in synthesis of polymers, drugs, pesticides, other valuable chemicals, ethanol, acetic acid, ethylene glycol, and vinyl chloride. And I'm sure you will know more about this ethylene that being used as plant hormones, right? Okay, which being used to accelerate the ripening of fruit, right? And it's also being used as a common polymer through polymerizing the alkene. So basically, you will see the alkene monomer can be polymerized by a chain of reaction. So we call it as addition polymers. So it can produce several products through this process. And for example, polyolefins is the polymers that made from monofunctional, single functional group. for example, ethylene and propylene. Right. So these are examples of products that come from ethylene. So ethylene had been used to produce several products such as textiles, right, paint and inks, plastic bags and bottles, agriculture products, right, diapers and children's toys, wood treatments, tires and automotive products, cosmetics, in electronics, and as well as pharmaceuticals. Okay, we look on how these products are produced, right, from ethylene. Okay, so we look in the middle here, ethylene, C double bond with 4 hydrogen link, right? So if you look the upper part, if it's oxidized, so it will form acetaldehyde, right? And if it's further oxidized, it become acetic acid. Okay, so if you look on the right, left hand side, if it's polymerized, it become polyethylene. On the left below, you can see if you add oxygen and with the agentum as a catalyst, it produces ethylene oxide. And if further being reduced with presence of water, right, it become ethylene glycol, right? So then below, you can see how ethylene, when it's with the presence of a catalyst and water, become ethanol, right? And the right hand side, when the presence of chloride, it become ethylene dichloride. And if you add further sodium hydroxide, it become vinyl chloride. So this is how the product of 2 carbon compounds are produced from ethylene, right? So I'm sure you are familiar with some of this product, right? Which is actually initially come from ethylene. So next is propylene, right? That is a methyl, one of the carbon. So we call it propylene. So this propylene are also important or intermediate in commercial products. So if you look on the right hand side, if it's undergo polymerization, so it will produce polypropylene. So I'm sure you have heard this polypropylene, plastic that we use. And then on the left hand side, when you add oxygen and the presence of agentum as a catalyst, it produces propylene oxide. And if you further reduce and add water, it becomes propylene glycol. Below, propylene in the presence of water and catalyst become isopropyl alcohol, right? And if it's further added with oxygen and catalyst, become acetone. So these are all common products in the form of 3 carbon compounds. Okay. Other than that, this propylene and other products or the based on the production of the ethylene can be undergo addition polymers. Okay, so meaning it is as a monomer. So for example, the first one, propylene as a monomer, I has mentioned earlier, it can produce polypropylene through polymerization of the monomer. For example, like vinyl chloride, when it's polymerized, it becomes polyvinyl chloride, the PVC, right? And the bottom is tetrafluoroethylene. Okay. When it's further polymerized, it will produce polytetrafluoroethylene or PTFE or Teflon. I'm sure you have familiar with this product as well. Okay, so the stability of this alkene. So many reaction provides the opportunity for double bonds to rearrange to more stable isomers. So the question is how this alkene is stabilized, right? So it depends on its structure. So basically you can see it's through hydrogenation, right? Where the alkene is treated with hydrogen in the presence of, for example, platinum as catalyst. So where the hydrogen will add to the double bond. So it reduces the alkene to alkene, become more stable, right? So you can see that the process need lower heat of hydrogenation, which it corresponds to lower energy and greater stability of this alkene. So most stable double bond are those with the most alkyl groups. So we know that when there is an alkyl group, it is as electron donating, where they contribute to electron density to the pi bond. And this bulky substituent, like the alkyl group, are the best substituted as part of the structure. Okay, so when you look below the differences of the alkene hydrogenation, so you can see that the most substituted double bond, for example, okay, on the this is on the upper part is 3-methyl-1-butene, right? Below is 2-methyl-2-butene. So you can see that 2-methyl-2-butene, it has more substituent, right? So you can see that the heat of hydrogenation is lower as compared to the double bonds that have less substituent, right? So molar heat of hydrogenation of alkenes. So these are the list. So you can see the what we call this, the heat of hydrogenation from what we call ethene, propene, right? So it depends on the substituent. Okay, so 1-butene, right, or around 30. But you can see 8 ethyne, 3 double bond is the highest, right? Because of the very strong triple bond, right? Then followed by propine and so on. Okay. So you can see also when there are extra double bond, there is increasing in the heat of hydrogenation. So physical properties of alkene. So it has low boiling points with the increasing with mass. Okay, so the branch alkenes have lower boiling points. So then it's less dense than water. So it's lightly polar because of the pi bond is polarizable. So it has the intentioness to dipole with the water, right? Interaction. So alkyl groups are electron donating. So toward the pi bond, so they may have small dipole moment. So insoluble in water, but soluble in non-polar solvents. For example, hexane, gasoline, halogenated solvent, and ethers. Right. So the physical properties of alkenes. So the pi bonds, electrons not held as tight as sigma bond. So therefore, alkenes are more polarizable than alkane. So cis generally more polar than trans, and then trans lower the boiling point, right? So I think we did discuss about the cis and trans before on the structure. So more carbon groups will attach to the double bond, will have higher boiling point, right? So the density will be similar with the alkene. So trans higher melting point than cis. So because of the molecules are more symmetrical and packed better. Right. So now we look on double bonds on ketones and aldehydes. Okay, double bonds, carbonyl as functional group. So C double bond O group plays a particular important role in organic chemistry. So this group we call it carbonyl. Okay, some of the functional group based on carbonyl, okay, is shown below. So you can see aldehyde has a carbonyl, ketone, right? Acyl chloride, carboxylic acid, ester, and amide. Okay, so these examples, acetaldehyde, acetone, Okay, acetyl chloride, acetic acid, methyl acetate, and acetamide. Right, so we look on ketones and aldehydes. So we know ketones, two alkyl groups that bond to a carbonyl group, right? And aldehyde, only one alkyl group. Okay. So the simplest carbonyl compounds are ketones and aldehyde. So you can see on the structure on the left is formaldehyde, is the simplest aldehyde with 2 hydrogen atom, okay, bonded to the carbonyl group. So it has similar structures and similar properties, but with a few exceptions. So it has some differences. So most cases, aldehyde are more reactive than ketone. I think you know why, because of the hydrogen, right? Okay, so for example here, aldehyde. So this can be hydrogen or hydrocarbon group, or R. Okay, all aldehyde have a hydrogen attached to the carbonate, and this for ketone both be hydrocarbon group. So usually it's not that reactive, right? Because of the R group is hydrocarbon. So structure of the carbonyl group. Okay, so the length, for example, ketone is 1.23 angstrom. Right, is shorter than the alkene, right? Which is carbon and carbon. So carbon and oxygen will have lower, and the energy is higher. Okay, as compared, you can see that the carbon sp2 hybridized and the carbon oxygen bond is shorter, stronger, and more polar than the carbon-carbon bond in alkenes. Right. So this is aldehyde and ketone. So on the left is aldehyde. So you can see both have the same angle, 120, right? Both have this sp2 hybridization on the carbonyl. Okay. So the we can see that this structure very polar. Carbon double bond or carbonyl has higher boiling point than alkanes. The hydrogen bond acceptor make it as soluble in polar solvent, and there is no hydrogen bond donor, so it will cause the boiling point to be lower than alcohol. So the nomenclature for ketone, so we look on the left hand side first. So we call this as 3-methyl, right, 2-butanol, right? And on the right hand side, 4-hydroxyl, okay, 3-methyl, 2-butanol. So the number of chain, so that carbon has the lowest number. So, and then we will replace with the alkane with on. Instead of E, change it into O and E. Right, ketone nomenclature continued. So for cyclic ketone, so the carbonyl carbon is assigned the number 1. So it become 3-bromocyclohexanol. So this is another example. So aldehyde carbon is number 1. So replace E with al, right? So the name for this structure is 3-methyl pentanal. Right. So the carbonyl as substituent. So one on a molecule with a higher priority functional group, a ketone is an oxo, and aldehyde is a formyl group. So aldehydes have a higher priority than ketones. Okay, so this is example of 3-methyl 4-oxopentanal, right? And then this one is 3-formyl benzoic acid. So common name for ketones, so name as alkyl attached to carbon double bond or the carbonyl. So usually we use Greek letters instead of numbers. So on the left is methyl isopropyl ketone. So if there is bromine, it become alpha bromo ethyl isopropyl ketone, right? So we use Greek letters. Historical common names. So these are common structure that you found or may heard had been used in commercial products, for example, like acetone, acetophenone, okay, and then benzophenone. So boiling points for ketone and aldehydes, they are more polar, so they have higher boiling point than comparable alkanes or ethers. So they cannot hydrogen bond to each other. So their boiling point is lower than comparable alcohol. So butane is 0 degree, and then methoxyethane is around 8 degrees Celsius. Then continued by propanol, boiling point is 49, and then increased to acetone 56, and lastly 1-propanol is around 97 degrees. So it's almost like water, and almost 100 degrees Celsius. Okay, the solubility of ketones and aldehydes. So it become a good solvent for alcohol, right? Because it has a lone pair of electrons on oxygen of carbonyl, which can accept a hydrogen bond from OH or from NH. So acetone and aldehyde are miscible in water. I'm sure you know that this acetone and acetaldehyde can easily dissolve in water, right? In formaldehyde. So so it actually comes from example trioxane. When it's heat up to produce formaldehyde, and further in the presence of water become formalin. So this formaldehyde is gas at room temperature, but when you add water, it becomes formalin, okay, which is a 40% aqueous solution. Then for the infrared spectroscopy, so the ketone and this aldehyde, right? So they are very strong in carbon double bond stretch around 1710 centimeter. And then the additional of the carbon hydrogen stretches for aldehyde with 2 absorptions at 2710 and 2810, right? Centimeter per centimeter. Okay, and the IR spectra. So this one, if you look under the UV spectra, right? The position, okay, the conjugation lowers the carbonyl stretching frequency to about 1685, okay, centimeter over centimeter. So rings that have ring strain have higher carbonyl frequencies, right? So you look here the structure. So acetophenone 1685, right? It increases to 1690 when it becomes 2-butanol, and increases further when it becomes cyclopentanone and cyclopropanone, right? So the industrial importance of acetone and methyl ethyl ketone are important solvents. So formaldehyde is used in polymers like bakelite, right? And then flavoring and additive like vanilla, cinnamon, and artificial butter. Okay, so this is to show you the structure of ketones and aldehydes used in household products. For example, butyraldehyde, which use in margarine and foods. Okay, vanillin, I'm sure you know, is a vanilla, foods and perfume. Acetophenone, pistachio and ice cream and cinnamon, candy, foods and drugs. I'm sure you have also familiar with camphor, right? That we use in liniments and inhalants, right? Pyrethrin, right? So we use in plant insecticide. This is Yavon, enantiomer of carbon, right? That's in spearmint and caraway seed. So used in candy, toothpaste, and lastly, musky aroma, used in perfumes. Right? So we have seen how the synthesis or the production of products from ethylene. So we want to see also how this synthesis of ketones, which is from carboxylic acid, right? So if you look the process from cyclohexane, which is carboxylic acid, the presence of phenyllithium, it convert to anion, and the hydronium ion and become hydrate, and lastly to produce cyclohexyl phenylketone. So the organolithium will attack the lithium salts of carboxylate and ion to give dianions, which then protonation of this dianion, okay, form the hydrate of a ketone, which can quickly lose water, okay, to form ketone. So ketones from nitrile. So you can see the structure here, right? So this is a Grignard or organolithium reagent, which can attack the carbon of the nitrile. Then the imine is then hydrolyzed to form a ketone, become a magnesium salt of imine, and then become imine with the hydrogen and hydrogen ion, and lastly become ketone and release ammonia. Then production of aldehydes from acid chloride. So we have acid chloride here. So the lithium aluminium tributoxyhydride is a milder reducing agent that can react faster with acid chloride than with the aldehyde. So from acid chloride, it straight away will produce into converted into aldehyde with the presence of this lithium T-butoxy, okay, of this hydride. Right. Then this nucleophilic addition, which a strong nucleophile attacks the carbon, which can form this alkoxide ion, okay, and then it protonated to produce this aldehyde, which is more reactive than ketone. So hydration of ketones and aldehyde. So for example, acetone with the presence of water become acetone hydrate. So in an aqueous solution, ketone or aldehyde is equilibrium with its hydrate, become a germinal diol. With ketones, the equilibrium will favors the unhydrated ketone form and become carbonyl. Right, so the mechanism of hydration of ketones and aldehydes. So you look on this carbonyl structure, right? So with the hydration occurs through the nucleophilic addition. So the mechanism with water in acid or the hydroxide in base. So it will serve as nucleophile. Right. So this is where the reaction occurred on the, for example, when the presence of water, like will attack on the carbon, and then on when the addition of oxygen to the carbon, right, further it produce and then release hydronium ion. Oxidation of aldehyde. So there is a possibility of aldehyde to be oxidized, right? So for example, isobutyryl aldehyde, when it's oxidized, it forms isobutyric acid, right? So basically aldehyde, when it's oxidized, it can easily form carboxylic acid. Right? Then deoxygenation of ketones and aldehyde. So the Clemmensen reduction or the Wolff-Kishner reduction can be used to deoxygenate the ketones, right? And the aldehydes. So you can see here from ketone, it become alcohol and later become methylene group due to the deoxygenation. So we can also see carboxylic acid and derivatives. So the common carboxylic acid usually come from citrus, right? Like for carboxylic acid, there is when it's ionized in water, become carboxylate ion, right? And carboxylic ester or thioester and amide and acyl phosphate. These are all the carboxylic acid derivative. Acid chloride and acid anhydride. So the functional group of carboxylic acid, okay, looks like it's similar like ketone and aldehyde, right? It has carbonyl and OH bonded to the same carbon. And then carboxyl group is usually written as COOH. So the aliphatic acid have an alkyl group which bonded, right? So we call it as COOH. And then the aromatic acid have an aryl group, and fatty acid are long chain aliphatic acid. Okay, so common name. So this one is alpha chloropropionic acid. Middle we call it as gamma aminobutyric acid, right? And then most right hand side is beta methylbutyric acid. So we follow this Greek order, right? From carbonyl as alpha, beta, gamma, delta, and epsilon, right? So there are many aliphatic acid that have historical name. So the position of substituent on the chain are labeled with Greek letters, right? Starting at the carbon attached to the carboxylic as carboxylic carbon. So IUPAC name. Okay, so these are several IUPAC name, like formic acid, we call it methanoic acid. Acetic acid, the IUPAC name is ethanoic acid, right? So these are several names, okay, of the carboxylic acid, right? And the removal the final E from alkane name and add the ending with oic acid, right? So the carbon of the carboxyl group is the carbon number 1. So you can see all this acid. We consider carbonyl of the structure as carbon number 1. Okay, unsaturated acid. So removal the final E from alkene name at the ending oic acid. Okay, so for example here, 4-methyl-3-hexanoic acid. Right, so new IUPAC name is 4-methyl-hexy-3-enoic acid. So I'm sure you know what's the meaning of E, and the other one is E3-phenyl-prop-3-enoic acid or cinnamic acid. Right. Okay. So there are also aromatic acid, for example, like benzoic acid, aminobenzoic acid, or we call it orthohydroxybenzoic acid, right? Or p-methyl benzoic acid and alpha naphthoic acid. So these aromatic acid are named as derivative of benzoic acid. So we call auto, meta, or para prefix are used to specify the location of a second substituent. Okay, so the numbers are used to specify location when more than 2 substituents are present. Right. So then we look on dicarboxylic acid. Okay, so the aliphatic diacid are usually called by their common names. So for IUPAC name, number the chain from the end closest to a substituent. So for example, this structure, so we call it as 3-bromohexanidioic acid or beta-bromoadipic acid. Right. So we will also look at the boiling points of the acid. So the hydrogen bonded acid dimer will be formed. So it will cause the boiling point to be increased, and then similar alcohol due to the formation of hydrogen bonded dimer. This is how the structure of hydrogen bonded acid dimer form that cause the boiling point to increase. Then the melting points, the aliphatic acid with more than 8 carbon are solid at room temperature. Then the double bond, especially cis, lower the melting point. The following acid all have 18 carbon. For example, like stearic acid is saturated around 72 degrees Celsius. Oleic acid, which is 1 cis double bond, is lower, right? And this linoleic acid with 2 cis double bond even lowest, -5 degrees. Right, and then the solubility. So water solubility will decrease with the length of the carbon chain with up to 4 carbon. So the acid is miscible in water, very soluble in alcohol. So also soluble in relatively non-polar solvent like chloroforms, because the hydrogen bonds of the dimer are not disrupted by the non-polar solvent. Right. And then the acidity of the carboxylic acid. So I'm sure you are familiar with this formula, Ka, right? pKa, negative log of Ka. So the carboxylic acid may dissociate in water to give a proton and a carboxylate ion, right? So the equilibrium constant, the Ka for this reaction is called the acid dissociation constant. So the acid will be mostly dissociated if the pH of the solution is higher, okay, than the pKa of the acid. So this will occur when you do titration with base, right? So when you add base, so the acid will be dissociated, right? So acetate ion structure. So each oxygen atom bears half of the negative charge, right? You can see here, half. And then the delocalization of the negative charge over the two oxygen makes the acetate ion more stable than the alkoxide ion. Right. And then the aromatic carboxylic acid. So the electron withdrawing group will enhance the acid. So you see from methoxy to benzoic acid to nitro to meta to p-nitro to auto is increasing, right? Become very strong acid, stronger the acid strength, and the electron donating group will be decreased. The acid strength effects are strongest for substituent in the auto and para position. Okay. So deprotonation of carboxylic acid. So the hydroxide or ion deprotonated. Okay. So the acid to form the carboxylate salt. Okay. When you add strong base. So adding a strong acid like HCl regenerate the carboxylic acid. So later when you add further strong acid, so it will regenerate the carboxylic acid. So deprotonation of carboxylic acid. The hydroxide ion deprotonates the acid to form acid salt, right? And adding a mineral acid regenerate the carboxylic acid. So this is how in commercial where they add acid salt, right? You can regenerate the acid. For example, sodium acetate to become acetic acid when you add HCl. Okay. Naming of the carboxylic acid salt. So the first name, the cation. So then name an ion by replacing the IC acid with 8 ATE. Okay. Potassium 3 chloropentanoate. Right. And then the properties of acid salt. So usually with no order, it's solid. It's a carboxylate salt of sodium, potassium, or lithium, and this ammonium ion are soluble in water. Soap is the soluble sodium salt of a long chain fatty acid. So, and then the salt can be formed by the reaction of the acid with the sodium hydrogen carbonate, releasing the carbon dioxide. Okay, so hydrolysis of fats and oil. And this is basis hydrolysis, right? So you can see this example of triglyceride, right? Through undergo hydrolysis, so it will release the glycerol and 3 fatty acid, right? So the basic hydrolysis, which you have done it in the reaction, we call it saponification. Okay, and then some important acid, the acetic acid is the vinegar and other food that used in industrial as solvent and catalyst, and also reagent for synthesis. And we know fatty acid from fats and oils. Benzoic acid is found in drugs and preservative. Adipic acid is used in to make a nylon 66, and phytalic acid, which is used to make polyesters. Right. So these are some of examples that product from acids. Okay, and then oxidation. Okay, so the primary alcohol to form the carboxylic acid to become aldehyde, and then lastly carboxylic acid. Example 3-phenylpropanol, right? With the presence of this sulfuric acid and sodium chromium oxide, it produces 3-phenylpropanoic acid. So you can see that the potassium permanganate is occasionally used but the yields are often lower, right? And then hydrolysis of nitriles. So basic or acidic hydrolysis of nitrile produce carboxylic acid. And then the overall reaction starting from alkyl halide, okay, adds an extra carbon to the molecule, right? So you can see the structure, the aromatic structure of CH2, bromine, right? And then there is presence of the nitroacetone, right? So produce lastly become in the presence of water and reduce with hydrogen. Right? So now it becomes CH2CO2H, right? The substituent. So you look that there is an extra carbon that being added to the molecule. So acid derivative, the group bonded to acid group to determine the class of compounds. So OH as a carboxylic acid, Cl acid chloride. If there is a oxygen and any group, or we call it the hydrocarbon, or we call it ester, and H2 as amide. So this interconvert via nucleophilic acid substitution, right? And then nucleophilic acid substitution. So you can see example carboxylic acid, acyl halide, and hydride, ester, and amide. So carboxylic acid will react by nucleophilic acid substitution, where one nucleophile will replace another on the acyl or the carbonyl, C double bond O of the carbon atom. All right, also, that is actually the last slide for this topic. I know it's very long, but I have to cover, as I said, on the double and triple bonds, as well as the acid derivative. So I hope you can follow and go through the slide again. And because of the, I will ask question basically based from the notes, right, that I given to you last week and also this week for your final letter. All right. So if, do you have any question? Guys, are you still there? Because we couldn't have any, yeah. I stop sharing first. Okay, any question?
No, doctor.
No, doctor.
So if no question, can we dismiss early, like 1 hour early before 12?
Can, doctor.
All right, thank you so much for your attendance. Yep. Don't forget to tick on your attendance in the Putra Blast. If you forgot, just WhatsApp me to help you to tick, right, to check your attendance today. All right.
All right, doctor.
Okay, thank you so much.
Thank
Thank you, doctor.
Thank you, doctor.
Right.
Thank you, doctor.
Thank you, doctor.
Welcome. Right, thank you.
Thank you, doctor.